Hello, everyone, and welcome back to the Hyperthesis. We are here now at the episode 22. It's a very special episode because we have a guest again today, Mr. Pablo Scrosati. All right, my name is Pheely.
I'm Patrick.
I'm Liam.
Woo! And I'm Pablo.
All right, so welcome, Pablo, to the Hyperthesis. So today, our main topic is going to be on Pablo's stuff. So he's doing chemistry. So this is going to be a little different than the bunch of physicists discussing how we think nature works. But before that, let's discuss what's been new for everyone here. What's news? Anybody want to have a take?
Well, just not so much news, but something I just want to kind of open the discussion to is the benefits of open source software. So just anecdotally, in earth sciences, we use programs called geographic information systems. And these are used to essentially manipulate and analyze different types of maps, very generally. But they're very powerful systems and very powerful pieces of software. And a lot of them tend to be behind some sort of paywall. And given that it's used in industry a lot and academia a lot, these are very, very steep paywalls. Like the one that comes to mind is the ArcGIS program, which is extremely expensive. Most universities offer it for free for students, but even then it's almost prohibitively expensive unless you're a company that needs to use it every day. Now, within recent years, there's been a very big open source movement with this type of software, introducing things like quantum GIS or quantum geographic information systems, which is an open source software and, in my opinion, is just as good and sometimes even better because people can contribute to it. And this is something I found with a lot of different things like IDEs for different programming languages or even different types of software that I used in particle physics like Root, which is made by CERN, where it's all open source software. So that means people can make customized packages for it. It's not behind a paywall and there's not, say, patented trade secrets in which you can't access the code. And it's just incredible the level of detail that you can add to a program as something that's open source.
Well, yes. I mean, most of the programs I use for my research are open source, or actually open source also have their own license. For software, you can have like GNU license, and you have the other one. I'm not quite sure. I'm not a software developer, but there are these huge community of people who want to implement and support your programs. Like, oh, you need help writing subroutines and stuff. I think it's really nice. But there's also merit in commercial products also that, oh, you want to make it better. You have more funding. There are merits in having closed system too, but open source is a good way to go. And I realized I haven't done much of the intro topics at all. So today I also have the other one that I've been thinking about. I talked to Liam a little bit about this. I was in the theory club. I was talking about hysteresis. And for those who don't know, hysteresis is basically when system have a memory, they can remember what happened in the past. Basically, there's an easy explanation. That makes me one thing that makes me think is about hysteresis is a delay. So if there's a delay between input and output of the system is called to have a memory. If you think of hard drive, right? With your hard drive, you change the magnetic state of the actual disk or the part of the disk to remember the data. But eventually, those things would go away because those things don't last forever. And that's what made me think about the brain. That our memories are just because our brain is lacking to keep up with the present. So we got stuck in the past. So, well, how do you move on? Well, you just forget because memories are just the brain's delay to keep up with the future, with the present.
Is hysteresis, I know we studied this a little bit during our undergrad, and I always just assumed this was the case, but I don't actually know. So, like, when you store information on a computer, turn your computer off, you unplug it, whatever. I'm assuming hysteresis is, or something similar, is why the information that's stored in the computer stays the way it does. I don't actually know.
So, from my understanding, is that computer storage, is, in particular hard disk drives, because solid state drives are very different, but for hard disk drives, it's not so much hysteresis that's happening, but it's just that you have different magnetic orientations on the disk, and those correspond to either a 1 or a 0. So if it's, say, the magnetic field is pointing down, then it's a 0. If it's pointing up, it's a 1. And so since it's some sort of paramagnetic material in the disk, then those stay because those domains have no other reason to change. Whereas hysteresis is, and I may be getting this a bit wrong, but hysteresis is where you actually have those domains changing or keeping the memory over time, even under changing conditions.
Well, I think most of the time we talk about magnetic hysteresis in physics, but hysteresis also have like classical hysteresis and other type of hysteresis, and in control or in engineering, in skier system machines, where hysteresis just mean delay, right? Delay in a system. There's a delay between input and output.
Yeah, it's actually funny you mentioned this because like about a week ago, I had a group meeting presentation in my with my group, and I was showing some electrochem curves. And I don't know how familiar you are with these electrochem curves, but there's sort of a classic duck shape that you get from them. And basically, the curve as you move to a positive potential does not match the same one as you move to a negative. And my supervisor was there going, well, how do you describe this? And I was like, well, there's basically something happens and the system's not responding fast enough. And so you get a slightly different thing. And then on the way back, it's sort of the opposite effect. And he says, yeah, his hysteresis. It's like, oh, interesting. So when you brought this up, I was like, oh my goodness, I cannot believe that this happened to me last week. And all of a sudden now it's even somewhat relevant in a conversation I'm going to have outside of this, but sort of an aside, not really super related to your hard drive topic, but yeah.
Well, that's what happened a lot, right? I think what you talk about electrochem is basically, I think, might be some type of hysteresis too, because there's a delay between the system to catch up with whatever field or force that happened to it, which happened a lot, right? If you think of cars, when you start the engine right away, it's not like you transfer the engine from input to output right away. You have to start the engine for things to happen. And my point that blew my mind was that, we think about the brain as like, we're supposed to be in the present always as human. We live in the present, but our memory is because our brain is lagging behind. If you think about computers, they're always in the present, but we introduce this artificial memory by hard drive, by having RAM, by having stuff to store stuff, to be able to be useful. But in essence of being in the present, it's just like, we just perform calculation right away. So maybe for people who are don't want to move on from relationships, just forget. Anyways, so I think that's a good for the introduction topics. So now we're getting to the meat of this episode. So we're going to be talking about Pablo and what he does. So to get a little background, so Pablo is doing a PhD in chemistry at the University of Western Ontario. But I will let him introduce himself about what he does on the project and what he is interested in, what his hopes and dreams. Pablo, take it away.
Well, thank you for the introduction. I guess I could have led this off a little earlier, but it's really good to be on the show because I started listening to it after Pheely introduced it, and I was telling Liam a little bit in some preamble that I think it's an exceptionally well-produced show, given that it's a couple of graduate students putting it all together, so hats off to you. So as Pheely said, yes, I'm a PhD student at the University of Western Ontario studying in chemistry, formerly in physical and analytical chem. My main studies or focus areas are essentially using mass spectrometry to probe different types of protein functions and behaviors, as well as implement additional analytical techniques so that we can sort of enhance what the classical ways that we the classical methods that we use in chemistry to look at proteins. On top of that, I also dabble a little bit into some molecular dynamics simulations, but that's mostly to augment what we do experimentally. And as for the hopes and dreams part of this, I guess I eventually want to end up working in some research and development, specifically with pharmaceuticals, protein-based pharmaceuticals. Yeah, I could go on about this stuff here, but I'll leave that brief for now. And if we get to it, then we'll get to it.
I remember visiting your lab once, a few years ago, and you were doing some spectrography stuff, right? And that area is actually, I thought it was like, it's really similar to physics lab. A lot of people do X-ray diffraction or things to figure out the structure of the system. So as a chemist, do you have to learn a lot of physics when you work in those type of field?
I will say that the physics aspect of things is not nearly as, it's not as technical as, how should I put this? I guess let me use the example of X-ray crystallography that you brought up, because that has a huge portion of physics and math and numbers behind it that go into calculating what these structures are. But for us as chemists, the important bit that we care about, and if we were to answer questions for advisors or whatever, is that you end up with crystals, you shine light through them, some diffraction pattern forms, and through a series of mathematical transformations, you're able to figure out where these high regions of density are that then lead to a structure. So in terms of the physics, I would put it as a very vague understanding of this, and it's more the practical and applied aspect that is important to us.
Mm-hmm. Yeah, because last guest we had was Scott, who also used what's called XD, the X-ray stuff to analyze the structure of the system too, but he did more on lithium batteries and all this stuff. But I think for physicists, we also care a lot about developing those type of technology rather than using it too, because I know some of my colleagues have this type of spectrography technique that we're developing instead of they don't care what they look at, but they'll just say they just try to get higher and higher resolution and better precision.
I have to say that I'm very thankful to the physicists who figure this stuff out, because we wind up trusting a lot of the theory behind this, sometimes more blindly than I think we should. But when we get a crystal and we submit it to the lab for them to find the structure or whatever we care about, they give us a report back, and we basically take that data and use it as it is. But the huge amount of work that went into figuring this stuff out is more or less just now embedded in some software or some couple of clicks, or I guess it can get more technical the more complex of a system that you get. But at the end of the day, this stuff is entirely only possible because the physicists figured out how this stuff works, and we're just taking advantage of this.
I think something similar happens with the field of density functional theory, where a lot of physicists come up with these models and they apply them in chemistry in these kind of simulations on how large amounts of atoms or molecules or whatever interact.
Yeah, I mean, the DFT stuff. We have a student, actually. I don't personally work with this, but we have a student who is attempting to sort of reconcile observations that are done using simplistic, I'll call them Newtonian models, on how protons should be placed inside of small peptides when you do gas phase simulations. But these are, like I said, based on these Newtonian models, so there's a lot of classical physics involved, some Coulombic terms. But the best way to do this sort of stuff would be some quantum mechanical aspect. And so they approach the DFT side to say, hey, does the structure that you get from DFT look like the structure we get in MD if we apply this stuff? But we've had countless sort of consultations with other professors who have a much more solid understanding of how this stuff works, so that when we say, hey, we clicked these settings over here, we have these basis sets, we have all this stuff, and then we hit run, is that good? Is that bad? We don't really know. But of course, there are people who do really know this stuff.
So you said you study proteins, and to me, proteins are interesting because a lot of people study it, and is maybe well, it is like a fundamental, almost like unit of life too. And one word or like phrase I heard a lot in study protein is protein folding. I don't know. Are you into like the well in your research? Do you care about protein folding? Like, do that matter, or is it like anything related at all?
Quickly before you answer that, I know very little about this stuff, and maybe people listening are like me as well. So, very quickly, if you could summarize it, what is a protein from like a chemical
Yeah.
point of view?
Yeah. So, quite simply, a protein is just an amalgamation of small molecules called amino acids. They're linked together to form these big chains. And these big chains, depending on the amino acid, have different properties. And so they tend to form sort of interactions amongst themselves. And you get one final structure that is the definition of your protein. So a bunch of amino acids make a huge peptide. That peptide, having folded into its final structure, is the protein. And what these things do is they have all kinds of functions. I mean, the list really is just as Pheely had said that they do quite literally everything in the body. So, yeah, I don't want to go out and say that, oh, they do this or they do that, because they're truly remarkable things that have all kinds of different applications. Yeah. To go on Pheely's question here, do I care about protein folding? The short answer is yes, and the longer answer is I don't personally try to understand the intricate mechanisms that take these amino acids and put them into the final protein structure. So I kind of glossed over that with Liam's quick comment, suggestion, or cue there. And I just said, hey, these amino acid chains, they will form these peptides, these peptide chains that will fold into their final proteins. I don't personally look at that. There's a whole lot of work that goes into figuring out these intricate complexities, but my area of research is more on now the fact that a protein can do these, or a peptide can fold into these final structures, means that it has to have some sort of dynamic component to it. And if we can start to figure out the dynamics that are associated with the final product, we can start to understand, or hopefully see, interactions that are at play that would drive towards more energetically favorable structures. Because if we think about all proteins, the fact is they're in that state because they're energetically favorable under those conditions. So somehow something is driving them. So if we can look at the parts that are guiding that at the end product, we can start to get some idea of what's going on during the process.
Well, since my field in my group, part of it also has a lot on research on self-assembly and how solid structure form crystalline structures and lattice. What you said is really interesting because you said energetically favorable. To us, it's like, oh, it has the lowest free energy, right? It's find the minimum free energy, or so the system start to self-assemble. But there also another way to do it is called entropically driven. So things can be driven by entropy, and it's kind of interesting to see this happen in a what's called a larger scale system. Maybe because the protein and amino acids in a way has a larger scale than you think about tiny molecules and lattice forming, right? So that's be interesting to see if we could talk more at some point about like, yeah, maybe our research is a little related in terms of our groups, because there are people in my group who used to study these kind of self-assembly and finding new crystalline structure. Well, why can't you apply that to proteins?
Yeah, it's funny you say that, because there's a running joke amongst a lot of us as chemists, and that is, when you don't know the answer to why things happen, you just say entropy. And it's because, yeah, when you have all these enthalpic effects and whatever, there generally exists, whether in your first state and then you have some reaction, most of the time they exist at the end. So what is actually the driving factor? We summarize it all as free energies, but really a lot of the time it's entropic factors that drive something to do whatever.
Yeah, I think that's also pretty common in physics, where there's a famous kind of discussion between I completely forget the scientist, but it was one of these famous thermodynamics guys and another one or something. And he was basically like, yeah, you call it entropy because it covers all your bases, because no one really gets it, and it's easy to just be like, yeah, it's entropy. And I definitely hear that a lot in the physics community. And it's I think minimizing the energy and maximizing the entropy are kind of synonymous. Maybe I'm wrong there, but that's what I've always thought of it as.
Well, since I do a lot of statistical physics, we kind of look at things a little differently, especially my field that when we come to statistical physics through information theory. So it's not a conventional phenomenological way to think about statistical physics, which probably might be interested in looking into statistical mechanics. How it's like, well, there are actually theories that deal with these type of problems where you have a lot of particles or whatnot and how they arrange and how they form phases, right? And we look at the formal structure of that, there might be some clues because, like, people say, oh, you don't know what entropy is. Agree. There's a certain ambiguity or vagueness in terms of entropy. But to me, after a few years doing this, I have pretty good handle on what entropy does, even though, there are a lot of ambiguity about it.
Yeah, I think, like you said, it comes down to information. And that's also kind of relates to your hysteresis comment about the brain. During our undergraduate degree, a professor gave a talk where they studied the brain using statistical mechanics, and I thought that was an extremely interesting talk, and that's something maybe we should talk about in the future. I just thought it was such a cool talk to use this thing that you usually use for like quantum thermodynamics to study the brain, and like Pheely, you're using it to study like design and battleships and other systems. So it's really cool how you can apply to a lot of different things. But maybe we should take a step back. Speaking of our undergraduate university, maybe we should ask Pablo what got him into science in high school and the journey he took to get to where he is now, because we went to the same undergraduate university.
Yeah. Yeah. Well, in high school, it was sort of I'll call it a bit of a mess. So I did the IB program, the International Baccalaureate program, which, if anyone's listening to this and wondering if it's worth it, my experience is no, but I'll leave it at that. And you can talk to other people about it because I'm not going to get into the politics aspect behind it. But during that time, I did we have different electives and choices that we can take, and so there's people who chose to do sort of the physics aspect, and me in high school, like a lot of ambitious high schoolers, said, oh, I'm just going to be a doctor, no problem, easy peasy, this is a free path to that. So I said, I'm going to do biology and chemistry. So I did the biology. It was fine. A lot of it was ecology, which I'm not interested in. I prefer looking at the biochemistry and sort of microbiology aspects. But then the chemistry part was the part that I genuinely was excited to do. So I kept coming back to the chem class, and that stuff was always fun. Every part of it I thought was pretty interesting. But I was still young and naive, and I said, nope, still going to be a doctor. So what's the best way to be a doctor? Somehow I came to the conclusion that human kinetics was the proper choice. So I signed up to St. X, joined in human kinetics. I did that for a year and realized yet again that the only class I genuinely enjoyed going to was my Chem 100, my intro to chemistry. And it was at that point that after some consultation with some friends, they all said, sounds like you really hate everything but chemistry. So why don't you just do chemistry? And I said, hey, those are great suggestions. So in year 2 of my undergrad, I formally transferred out of human kinetics into Bachelor of Science in chemistry. I declared my major there. I started loading up on all the chemistry courses, and I had a lot of fun doing that. And even though I don't study the topics, I even things like organic chem, a lot of the more hardcore physical chem, those were all a lot of fun and really enjoyable. So, that's sort of the path that took me there. And, after year 2, year 3 is a little bit more of the same, more complex. And then year 4 was the year that, I really got to learn about the very real world aspect and techniques of it, which sort of solidified everything that I thought I liked about it. So when you get to instrumentation, I feel like a lot of times in the early stages, like in year one, you're learning, oh, we can figure out this particle using this spectroscopy or using that. And it's sort of an abstract, vague thing. And then by the time you're finishing your undergrad, you've used all of that and you're saying, oh, wow, I did that myself. This was great. And that's what got me into wanting to do more of the analytical side of it. And I still had that little itch for the biochemistry aspect. And so that's kind of where I wound up with that.
So during those times, did you do research at all? Then how was the experience like?
In my undergrad, yeah, I did do research. So at the end of year two, I basically just pitched myself to a professor at Sinovax, and I said, "Hey, can I just be here doing volunteer work? Like, I don't need to do anything. I just want to learn stuff and be a helping hand." And he told me, "You know what? We actually have money to pay you. So how about instead of volunteering, you just work for me?" I said, "Hey, that sounds great." So I joined that. And it was in this year that I feel like I was given a lot of responsibility for what I was. Looking now as a grad student who supervises some undergrads, I'm looking at them and I'm thinking, wow, don't know if I would give them that same degree of task. So we had this 2-year project where we were basically studying the sort of stability of frozen lobster products. So I was doing a chemical aspect, but there was a huge component of it that was about basically how good does it taste? How does it smell? Because the point of this was to sort of help the lobster industry in Atlantic Canada. And yeah, so they told me, how much lobster do we need? How many reagents do we need? How long do you need to do this? And I said, oh, we're going to need to freeze it for a couple of years. It's going to cost this much money and I'm going to need all this stuff. And I basically just wrote down formulations. I gave it to my supervisor. He said, hey, this looks very good, very great. I thought, wow, this is a lot to do here. And that was how the research started, or my research started with, was with this project where, yeah, I got to do all kinds of very cool analysis.
I actually heard about that lobster project. At the time, I was studying supercooled water. So I heard there was, because freezing is actually kind of not exactly the word. Right? You're not freezing, you're supercooled the lobster so the crystalline structure of ice don't form and don't destroy the flavor. Because if you don't, people don't know the word supercool, it just means you cool it really fast. The crystal structure don't have time to form. So even though it's still water under 0 degrees, it's still liquid water in a way. So hopefully maybe that's the way to keep the flavor fresh.
I will just comment quickly. I was up in one of the chemistry labs doing some work, and all I distinctly remember is the smell of rotting lobster in the hallways. I think it was 1 or 2 days.
So on that, we did have to send emails out when we were going to be working on this stuff because it was quite putrid. I mean, you think it was bad in the hallways. Imagine being there. I would come home and my girlfriend would say, can you please take a shower? You smell like rotting seafood right now. And I said, yes, I just got home. Give me a second. I fully understand. It was a struggle. But yeah, on the supercooling aspect, yeah. So the point of this stuff was originally that, you know, in industry, it would be perfect to have a perfect product every time, but there are usually economic aspects that limit some whatever sector from being able to actually deliver that. And so in theory, that's where the competition comes in, but a lot of times it sort of stagnates. So the frozen lobster product that you get, especially overseas, is typically frozen, just putting it in a freezer with a little bit of salt solution. And so our goal was to take the aspects of freezing, as you said, that damage the product and attempt to alleviate that in a manner that was accessible to industry. So using cheap food grade reagents, are we able to stop or disrupt the crystalline structure that is known to cause damage to these products? And the other part of that was, can we do that through supercooling? So instead of freezing it by putting in a freezer where, you know, you give the water enough time to reorganize itself, form these huge lattices, can we freeze it using liquid nitrogen? So it's basically so fast that we get non-crystalline water. And so there were 2 combined aspects to that we wanted to test out, with the eventual goal being to have a solution that an industry could just essentially formulate, put inside, ship the product wherever, and it would be very cheap and not require complex freezing processes.
Yeah, one thing about water is that it is such a anomalous material where there's so many anomalies. So when you think about freezing, right, you think about any other liquid. Freezing makes things smaller because it's colder, things want to be tighter. But water, when it freezes, it expands. That's what the weird part. That's when we have a lot of water damage in things. When water seeps into cracks and it freezes, it expands, so the cracks widen. So a lot of water damage happen on the roads, on the things that happen actually like colder climate, like Canada. It's the water damage is really serious because this weird property of water itself that to me is like, well, that's give us all of us life. But water, even though it's one of the most common thing we see on Earth, it's one of the most anomalous material in the universe.
One of the weirder things. So that's like a pretty. I think that a lot of people can grasp around that. You say don't put glass bottles in the freezer full of water because it'll expand and crack. But a different aspect of freezing that during my time as an undergrad that I hadn't ever considered and then was starting to think, wow, this is true, is that it concentrates solutes. So if you have a tube of water and you expose it to something really cold, the inside's going to freeze it's going to take longer to freeze than the outside. And so as the outside of that starts to freeze, if you have something dissolved in there and you give the water enough time to sort of push that solute out, you'll end up driving whatever salt or other crap that you have in there towards the center. And so that can also be damaging in and of itself because you might be poisoning your systems. And it's something that I hadn't ever considered, but it's another thing of saying, when you freeze things, if it's really big, it doesn't matter if you submerge it in pure liquid nitrogen, the inside's going to take longer and you might be damaging that inside. And so somehow you need to address these problems.
Right, the temperature gradient is a big thing, like how freezing was formed. I think there's a big research in physics too on how freezing works, because as we know, there are more than 16 different types of ice. Because the ice we usually see is called hexagonal ice 6, I think. But there are other type. Ice in space, the crystal structure look very different, right? You still have like glassy ice where there's no crystalline structure, which we call amorphous ice. But water is such a fun and crazy topic. So, Patrick.
So, moving on from your undergraduate research and talking about what you're researching now, can you tell us, I guess, in more detail what exactly you're doing with proteins and I guess what the end goal is of your research, if that's clear at this point?
I work primarily with a protein called cytochrome C, and it's an interesting protein because I've mentioned now that you have these big amino acid chains and they form into a protein, but you can also get other things. You can get things that are stuck onto the sides of your proteins, either usually like antibodies, they can be like sugars essentially. You can have modifications that enable different things. And in the case of cytochrome C, there's a heme group on there, and it's basically this ring with an iron in the middle. And that iron is hugely important to its function because it moves an electron between two complexes in the respiratory chain. So it allows the generation of ATP, which is the energy currency in the body. And this protein in its canonical function is fantastic. It does a really good job at what it's supposed to do. But recently, it's also known to have other types of or other behavior, which seems to signal to the body that the cell needs to basically die. So that's the function of what's described as apoptosis. And the cytochrome C's inclusion in this is sort of unique because it requires the cytochrome C to undergo covalent modifications in order to achieve that. So the first work that I did was sort of characterizing how the cytochrome C with the iron under its two oxidation states, so where it has accepted an electron from one complex and where it has donated the electron to another complex, and how those things work. And during that initial project, I studied it using techniques called hydrogen deuterium exchange. And we found some really interesting things with that, which I can talk about separately, but I don't want to lose my full train of thought here. And so that was one part of it. And so now we're focused on saying, okay, So given that this is the behavior that exists in its canonical electron transport function, what happens to this small protein that all of a sudden triggers a huge cascade that says, hey, this cell is no longer viable and it basically essentially needs to die. So that's the part of the cytochrome C that I look at. And then due to COVID, when all our labs got shut down, I was just basically sent home, and my supervisor was looking at me and going, I don't really know what to tell you, because at this point I hadn't done any computational. The labs were closed, so I couldn't go in. I was like 4 months into my PhD, maybe 5 months. So it's not like I had data that I could just go out and publish it, or at least not new data that would have been worthwhile of a publication. So he said, hey, why don't you try looking at some molecular dynamics simulations? And so then out of a pandemic sort of project, I wound up doing MD simulations looking at liquid chromatography.
So for your MD stuff, like, is it like what type of software do you use? You use like LAMS or
we use
certain...
GROMACS. It's essentially just has a whole bunch of, it's a giant software package that's free to use. It has a whole bunch of different options that you can specify in there. It has a ton of very advanced features for establishing temperature, pressures, that kind of stuff. And it's very easily adapted so that we can sort of put in whatever molecule or system that we want, and we can visualize this. And then by changing essentially the parameters, we can generate simulations that at least we feel are very representative of the real world.
Oh, so what's the scale of simulation? Like 1,000 particles?
We typically are in the neighborhood of between 50,000 and 200,000 atoms.
Okay, so it's not a super real MD in the physics sense then, because like it's really hard to do anything more than, let's say, 100, 500 particles. So when you mentioned that these kind of external parameters like temperature, pressure, I was like, oh, now it's more like average or like a mean field simulation almost.
So just for these types of, I guess, simulations, you said atoms. So for example, for looking at proteins, are you modeling every single atom within that protein?
So we, in the old days, not that old, in the 2000s, when computers were not as fast as they are now, they used what are called united atom models. And basically, a CH3 group is pretty well known. The hydrogens on touch to that carbon don't do a whole lot. And so it was more computationally efficient to grab those 4 atoms and combine them into one that sort of more or less played as if it was the 4 of them described explicitly. In our group, we make it a very big priority that we always do what are called all atom simulations. So every single atom is modeled explicitly, and we try to put as few constraints on them as possible so that we are trying to model the real world in as great as detail as we can. Going any smaller than these big systems, a lot of times we don't get the detail or spatial resolution that we actually need. So for instance, if I were to cut down one of my LC systems from my 60 or so thousand atoms and I made it like 10,000 even, the issue with that is I wouldn't be able to see what my molecules are actually doing outside of just a very confined space. And so just their size, the amount of space that they need in order to fully move around and do whatever they're going to do requires that I expand systems towards areas that start to sort of shave off what's physically, I guess, represented.
So 50 to 200,000 atoms, like how many protein molecules would that be?
Yeah,
roughly.
So in these simulations that I conduct, it's usually one protein or peptide atom, a bunch of solvents, and then whatever in my chromatography, it's the support phases in chromatography. But just so you understand a little bit about what else the lab does, we focus on electrospray droplets, and so how those evolve during ionization processes. So those ones use significantly fewer atoms, but they are putting them essentially in a gas, in gas phase, or essentially in a vacuum. And so there's depending on the application that you need, you're usually just looking at the one protein or the one peptide or the one type of analyte, and it's surrounded by what we feel would be surrounded by in the real world, and that's what makes up the bulk of the atoms.
Just for those who may not be familiar with it, can you describe chromatography quickly?
Yeah, so chromatography, in the sense that I use it in, is a technique that essentially separates a bunch of different analytes of interest or molecules of interest using differential interactions with some supporting material versus some mobile material. So if we have molecule A and molecule B, and molecule A is very sticky to our supporting material, and we push liquid through it, molecule B will come out first, and then molecule A will come out. So we get the ability to separate, and then if we want to analyze it, we only have to look at one analyte at a time.
Well, I think you remember, like, in a more fundamental science class, right? Chromatography is when you see a bunch of colors that separates, like, in the material. So because chromas mean color, right? Chromatography, so you can see the color when you separate them. But that's the more of a easier, simple explanation. 'Cause I remember doing that in like school, like high school, even like middle school, right? Chromatography, but we didn't say chromatography. It's like, this is fun stuff. You add these something solution, and then start separating into different layers.
Yeah, I
Really
mean,
fun.
you're absolutely right. The problem with the chromatography we do is that these we often don't have any colors. So without we can't. And not only do we not have colors, sometimes we have so many different components, and then we need to extract them. Also, the evolution of these early chromatography days, where it's essentially describing the process behind it, is the advanced version, the high performance version, which involves very high pressures, all kinds of crazy liquids, and you're putting them inside of tubes and then shooting them out. And yeah, it goes from there. But yeah, that's, if you need a frame of reference, yeah, it's absolutely the separation of colors. And sure.
Yeah, but I was just thinking about other field, like Liam's more familiar with this quantum chromodynamics, right? It's like, we deal with colors in quantum, but it's like, those are not colors. They're just,
I don't know anything about that. Like, I'm aware it exists, but that's pretty much it.
That is definitely a particle
Yeah.
physics, but like heavy theory particle physics
It's like
stuff.
quarks and gluons and stuff like that. Like,
Yeah, my understanding of these colors in small scales basically cuts off at nanoparticles, and even then, when I hit these things and they say, "Oh, the size determines these colors," I stop understanding it very well.
So going back to, I guess, your modeling of these dynamics, are you also testing them in the real world? Like, are you taking these proteins and seeing if the models match the, I guess, real world experiments?
Yes. So I'm going to say it in this manner: the MD simulations that we conduct in our group are done in order to help explain what we see in the real world. So we are not relying solely on MD simulations to say this is what's going on. The best example of that are the MD simulations that other members of my group have done regarding these electrospray droplets. So for instance, under certain conditions, you inject a protein into a mass spectrometer and it's full of salt. And then under slightly different conditions, it has no salts on it. And so it's weird because the solutions are not the exact same, but they both contain salt, for instance. So why is it that one of them doesn't have it under some conditions and then you change them? And so we use the MD simulations, and it sort of reveals ionization mechanisms that that point to why there was no salt present in one spectrum and there was in the other spectrum, despite the fact that it was present in the same initial solution. So the MD is almost always done as a backup or as a way to help explain what we see experimentally.
I'm curious about the MD aspect too, because I work with a lot of people who do MD, and what the scale you're doing, it sounds like computationally impossible. Because in physics, to calculate 1 nanosecond of 1,000 particles, it takes a very long time. And when you say 60,000, because I'm wondering, like, are there some kind of cost grading techniques or something to make it faster? Because That's a lot of particle. Imagine each particle interact with every other particle. So there is a combinatorically large set of calculation that you need to do. So I don't know if you know anything about how they actually do the calculation, or are you just mostly using the package?
So I'm going to say a little bit about how I understand it, and then we can probably get more in depth into it. But because we are essentially looking at trajectories, we don't need to calculate explicitly energies at every single point. We just want to see how these particles are moving. So the energy is sort of implicit in that, but we want to know how these things move around essentially.
That's a big problem too, because imagine want to know one particle how it moves, right? You have to calculate the effects from 999 other particles for each one of them, and that's also have like a basically the chain reaction effect, right? If something changed a little bit, this what is so strange about these kind of calculations. There's so many calculations that it does depend on the scale that you want to do too, I think.
So there are, I mean, I'm not super familiar with this part, I'll say that right now, but there are cutoffs that we use where we stop treating interactions explicitly and we go into this mystical Fourier space where everybody just says, yes, it makes it faster and is very good, and we only need to have this level of resolution where we calculate things explicitly. The other speed up that we try to use, we typically use a 2 femtosecond time step. So we allow basically the velocities to act on the system for 2 femtoseconds, and then we recalculate forces and go from there. So I don't know how you and your simulations typically do that, but from what I understand, the 2 femtosecond is sort of the upper limit of where we can still be accurate enough that our results are acceptable, but definitely for people who care about small motions, the 2 is, I mean, even some bonds, because we treat them as springs, like a carbon-nitrogen bond, 2 femtoseconds is way too much, and if you tried to monitor the oscillation, you would never be able to see that.
So I'm curious, you're modeling, say, 2 femtosecond movements within your simulations, but in terms of the experiments, are you just looking at the final outcome versus the final outcome of the simulations, or are you actually monitoring across time your experiment?
So the simulations we always monitor across time because that's where we get the most detail of what's going on. So in the chromatography sense, when we want to see interactions with stationary phases, we need to be able to look at it and say the analyte started here, and then it had these temporary interactions with these residues, and then it unstuck, and then it moved itself around, some ion was bound to it, and then that triggered this and whatever. And in the experimental aspect, because a lot of times we can't just take microscopes and essentially look and freeze things in place, the results are hopefully that if in the MD simulation we see that there are more interactions with the stationary phase, that means it would have to spend less time in the mobile phase where it would elute. And so ideally and experimentally, we'll see that analyte came out later than an analyte that was less sticky. And so that's how we try to correlate these things. Now, we have techniques to be able to look at things more in detail around proteins. For instance, these hydrogen deuterium exchange experiments that I did, we also looked at that with molecular dynamics. And so what we were able to see is, because the HDX can pretty much locate down to the residue level where one single residue is more likely to exchange with a deuterium versus a hydrogen. I say deuterium, but this heavy water versus the regular, sorry, not heavy water, a heavy proton versus a regular proton. In the MD aspect of that, we can also get that same residue level resolution. And so we are able to directly monitor across time, even though the time regimes are usually a little bit different, what is happening MD-wise, and then also what is happening experimentally. We just have to tune our experiments in order to achieve that same level of detail.
Well, now it makes so much more sense that you work on a femtosecond scale, because I was talking about nanoseconds, and for reference, nanosecond is like a millionth femtosecond, right? So there's really different time scales, and it makes sense Because like in physics or in MD in general, we have other techniques like periodic boundary conditions to reduce this kind of like to have fewer molecules or whatnot. But for interest of time, I think this is pretty interesting. Pablo, you got comment?
Can I just say one more thing on your time scale thing? So these are our time steps, but we run our simulations for 1 microsecond in
That's
total.
long.
So it's however long as all of these small little procedural integrations until we hit 1 microsecond. And so on our newest system, which is with an RTX 3090 and a 12700K, that for some of my systems it takes about a week and a half to do.
Okay, that's really low computational power. We talk about computer clusters with supercomputer. Like 3090 is like ant, like it's nothing, right? It's small.
Yeah.
Because people who do these type of calculation, they actually do like computer clusters that have like huge RAM, huge CPU, huge GPU, and it takes a long time to get these results out. So I wonder what type of compromise that software has to actually do it. But anyways, in the interest of time, let's thank Pablo for this very insightful, interesting topic. And I think we could move on to the story. And before that, Patrick is going to tell us how to contact and reach out to us if you want.
Of course. So if you are listening to us, obviously you found the podcast. However, we are available on many different platforms, including Apple Music, Apple Podcast, Google Podcast, Amazon Music, Spotify. We're based out of Anchor.fm, and we can be found on most podcasting services. If you would like to reach out to us, whether if you have questions or comments, or you want to be a guest on the show, you can reach us at our Gmail account. So that's hyperthesispodcast@gmail.com. So you can send us any message you want, whether it's feedback or questions, and we will get back to you right away. We do also have an Instagram account at the Hyperthesis where you can get updates for when we post shows, as well as some behind-the-scenes look at our recording and our different processes that we use.
I don't know if Pablo wants to say anything to the listeners before we get to the story, or if he has any websites or wherever that you can
to plug.
I mean, yeah, I can plug some stuff, but before that, I wanted to take this opportunity and say thank you to all of you for hosting me. This has been great. I had a great time during this recording and also a little bit beforehand when we got to sit and chat a little bit more candidly. As for my sort of the plugs that I'm going to have, if you're interested in more of my work, my name is Pablo Scrosati. I'm at the Connerman Group at the University of Western Ontario. So Professor Lars Connerman does have a website there, and you can check out all the publications that come out of there, and you can see all the group members. And if you're interested in any graduate work, you can reach out to him, and hopefully that all works out well for you.
And if you have any questions for Pablo, is there a way to reach you, or would you rather they contact us?
No, they can reach me directly, preferably with my UWO email, so I'll give that. It's pscrosat@uwo.ca. And yeah, I love answering questions, so if you have anything, fire them my way.
There you go. So if you want to contact Pablo, whether you're interested in his research or interested in researching with him, go ahead and reach out to those different resources.
So today's story is going to be one of the most monumental figure in science and relate a lot to chemistry. And Patrick is going to be talking about it. So take it away.
Well, this monumental figure, just as an introduction, they are one of only 4 people who have won 2 Nobel Prizes. So that might obviously give it away right away. But they were born in Poland to a poor family and then slowly rose to such fame and renown that they got to the level of winning 2 separate Nobel Prizes. And their name is still remembered today. We have units of measurement relating to them. We have elements named after them. And this person is Marie Curie. Now, Marie Curie was born as Maria Skłodowska in Warsaw. So she was Polish, but at that time, Poland was still a part of the Russian Empire in 1867, the year of her birth. And she was the 5th and youngest child to her parents. Now, I wouldn't attempt to pronounce all of the names of her siblings and parents because I'm not that fluent in Polish pronunciation. But needless to say, her family was fairly large and they weren't very well off. They had lost many of their assets in supporting Polish independence, and unfortunately, Maria was born into a very poor family. Fortunately, though, her father was a teacher of math and physics, which helped inspire Maria to take an interest in those different topics. Now, during her younger years, her father was forced to take home different lab experiments since he was teaching at a high school, and the Russian, I guess, leaders at the time had banned any laboratory teachings in schools. And so Maria and her sisters were able to use this equipment and learn some basics of chemistry and physics and really got started with science from a young age. Now, it's also noted that at a young age, Maria lost 2 of her sisters and her mother, which led to some significant changes in her life, particularly dropping Catholicism to become agnostic, which, as we've heard from many stories in the past, it was actually pretty common for scientists in the 1800s and earlier to be quite religious. So this was something a little bit different. Now, like many of us, albeit under very different circumstances for the most part, high school, or at least the Russian level equivalent, was not kind to Maria. She did graduate with top honors, receiving a gold medal at the age of 15, but she suffered from depression afterwards, and it's said that she had some sort of collapse, and she went to go live with her family through the years after high school to try and recover from this. Now, her interest in mathematics and physics and chemistry couldn't be subdued even by depression, and so she wanted to attend university. However, at the time, universities had quite sexist policies, and she was unable to attend some of the main ones in Poland and Russia. However, she was able to attend a Polish kind of institution, not necessarily fully recognized worldwide, but it was still called the Flying or Floating University, that did allow women students. And this allowed her to continue her studies while still being able to work some different jobs. In particular, she worked jobs to help her sister pay for medical school, who then would return the favor later on. And she met someone who she fell madly in love with. Again, I will not try to pronounce their name, but they were a future well-known mathematician. Zurawski is their last name. So she fell in love with Zurawski, but their love was forbidden because she was poor, and his parents didn't want him to marry someone who was very poor and very out of it. Although it's said that he continued to think about her in his old age, sometimes staring at the statue of her that was erected at the university where he was a professor. So if that's not encouragement to go chase the person that you like, I don't think anything else is. So after this heartbreak for both Maria and apparently Zurawski, she continued to educate herself through both reading, so she taught herself a lot of the different concepts that she would later utilize, and she was also tutored in part. In 1890, she began training in a medical laboratory in Warsaw, and this laboratory was run by one of her cousins, who had previously worked as an assistant to Mendeleev, who is better known for his introduction of the periodic table and periodic elements and all of that work. Now, once she had saved enough money, Maria did move to Paris in 1891 and lived with her sister and brother-in-law, where she attended the University of Paris, studying physics, chemistry, and mathematics. So we have another chemist student. Here she became known as Marie, which is the French version of Maria, and she earned 2 degrees in quick succession, the first in physics and the second in chemistry just a year later. Now, her first true research involved studying the magnetic properties of various steels, and at this time where she was studying, she was looking for a larger laboratory because lab space, especially for women at the time, was unfortunately very limited. Now, this is where a man named Pierre Curie entered her life, And they were actually introduced by a mutual friend who had heard that Marie was looking for larger spaces and thought that Pierre might be able to do something about that. Now, Pierre was able to find a space for her, not his own, but he was able to pull some strings. And from there, their shared love of science brought them close together, where they eventually started to quite like each other. Now, she initially denied his first proposal, saying that she would move back to Poland and didn't want that life for him. But eventually he convinced her to move back to Paris full-time and pursue her PhD. And they were later married in July 1895. Now, the blue outfit that Marie wore to her wedding was actually in place of a bridal gown and would be the outfit she wore in her lab. So just imagine getting married in your lab coat. And that's pretty much what she did. Now, at the time, this was the very late 1800s, beginning of the 1900s, there was a lot of research around radioactivity, which was a very new topic at the time. So you had people like Becquerel who had made great leaps and bounds in actually defining radioactivity, as well as Röntgen, who discovered X-rays. Now, this inspired Marie to focus on work involving uranium rays for her PhD thesis. Now, using a device called an electrometer that was originally invented by her husband Pierre and his brother, she discovered that the air around uranium became electively conductive. And this further studies into this suggested that radiation from uranium came from the atom and not some sort of molecular interactions, which was what was previously thought. So this was pretty, I guess, paradigm shifting, because it was thought that radiation itself was just some sort of natural process between molecules, and that's about the depth they knew. Whereas now it was shown that, hey, there's actually something going on with the atoms. Now, also during this time of pivotal research, her daughter was born in 1897, with the following daughter being born in 1904. Now, Irene, her youngest daughter, and Eve, her oldest daughter, would go on to be successful in their careers. And Irene, in particular, went on to win the Nobel Prize in Chemistry for the discovery of artificial radioactivity in 1935. And she shared that with her husband. So we have a family of Nobel Prize winners here. Now, after this work, the Curies continued to work. However, they weren't well funded, and they worked in a very poorly ventilated shed. We now know that working with radioactivity and radioactive materials is dangerous, but at the time, nothing was really known about them, especially the health effects. In particular, they worked with pitchblende and tobernite, which are minerals containing uranium, and that eventually led to the discovery of thorium. They also discovered polonium, which they named after Poland, and radium, which was a radioactive substance. And they also did some medical research and found that radium destroyed tumor-forming cells faster than healthy cells, which is, I guess, a poor irony in this case, given the effects of radiation on Marie later in life. Now, in 1900, Marie became a faculty member at École Normale Supérieure and received her PhD in 1903. So she actually became a faculty member before getting her PhD. And for her PhD, she was supervised by Gabriel Lippmann. Now, Pierre and Marie, along with Becquerel, were awarded the Nobel Prize in Physics for the research into radiation phenomena. Becquerel, of course, being one of the first people to discuss and discover radiation. And this made Marie Curie the first person to win the Nobel Prize, or the first woman to win the Nobel Prize. Now, they were too busy with work to attend the actual ceremony, but they eventually gave their required lecture in 1905. And unfortunately, less than a year later, in 1906, Pierre Curie was killed by a horse-drawn carriage. Now, he had just become chair of physics at the University of Paris, so they instead offered that position to Marie, who filled her husband's role, and was determined to make a lab in her husband's name to honor him. Now, there were a couple of scandals that were grossly exaggerated by the press, especially given that she was a woman in science that was not necessarily highly regarded at the time, and we won't get into those. But in 1911, Somewhat controversially at the time, Curie won her second Nobel Prize, this time in chemistry, for the discovery of polonium and the discovery and isolation of radium. So, despite some protests from people involved with her, quote, scandal, unquote, she was successfully a 2-time Nobel Prize winner. Now, during World War I, she was very influential in developing X-ray systems, particularly mobile ones that would be used to treat soldiers, and it said that over 1 million soldiers were treated by her X-ray devices. After the war, she went on to found many different institutions that study radioactivity, and many of which still exist today. However, some of which were called radium or something to do with radioactivity, which have now been renamed after Marie Curie. Now, she died at the age of 66 in 1934 in Pheely from aplastic anemia, which is something that's caused or is believed to be caused by damage to her bone marrow caused from prolonged exposure to radiation. So unfortunately, the thing that she studied and that she was so intensely interested in ended up most likely being the thing that killed her. Now, both her remains and the remains of Pierre Curie were transferred to the Paris Pantheon, where they were sealed in a lead container due to their high radioactivity. But that's where they remain today. It's also noted that her notes, her cookbooks, almost everything that she was in constant contact with are now currently in lead-lined boxes and will be for the foreseeable future because of the fact that almost everything she touched became radioactive. And so it's dangerous, and now we know that it's dangerous thanks to her work. So Marie Curie is a remarkable scientist who paved the way for a lot of the studies and a lot of the knowledge that we know about radioactive substances. And she also discovered 3 separate substances. There is also curium, which is named after her. And I think this is truly one of the few people in the world whose legacy will continue to live on through many centuries, if not millennia, depending on where we end up. And I think she should be celebrated daily, but in everything we do, part of it is thanks to Marie Curie.
All right, thank you, Patrick, for this really interesting, insightful theory of actually the name that as all scientists are growing up learning science all have heard. But today, I think this is a very good day. All right. So I thank Patrick for the story, and thank Pablo for having this conversation with us. And I'll see you guys next week. Take care.
Bye, everyone.
See ya.
Bye. Thanks again.